So till now we have studied how to calculate moment of inertia of some standard shapes with respect to some standard axis of rotation. But what if we wish to calculate the moment of inertia of these standard shapes with respect to some other axis of rotation? Do we have to perform all the calculations starting from scratch, or there is a smarter way around? So let's try to look at it. Actually, there are two very powerful theorems which can simplify lots of our efforts, and these theorems are the perpendicular axis theorem and the parallel axis theorem. These two theorems are used to calculate the moment of inertia of a rigid body with respect to an axis of rotation if we know the moment of inertia of the rigid body with respect to some other axis of rotation. So this would be more clear as we move further. So let's start studying about these theorems. So let's start by understanding what is the perpendicular axis theorem. So first of all, there is a disclaimer that perpendicular axis theorem is applicable only to laminar bodies. And what do you mean by laminar bodies? By laminar bodies, we simply mean 2D structures or planar structures or planar bodies. That is, the bodies which lie in a single plane. So in this particular figure, we are given with a planar body, and these planar bodies are generally called as laminas. So here we are given with a lamina, and here in the lamina we have two axes. Let's call this x dash, and let's call this axis as y dash, which lie in the plane of the lamina, and these two axes are mutually perpendicular to each other. Now at the point of intersection of these two axes, there is a third axis. Let's call this z dash, which is perpendicular to the plane of the lamina and passing through the point of intersection of x dash and y dash. So what do we have? We have x dash perpendicular to y dash, but these two axes lie in the plane of the lamina, and there is a third axis z dash which pass through the point of intersection of x dash and y dash, and z dash is perpendicular to the plane of the lamina. So all the three axes x dash, y dash and z dash are mutually perpendicular to each other, and x dash and y dash is lying along the plane of the lamina, and z dash is perpendicular to the plane of the lamina. Now let us assume the moment of inertia of this lamina about the axis x dash as ix, the moment of inertia of this body about axis y dash is, let's say, iy, and let us say that the moment of inertia of this body with respect to z dash be iz. So according to perpendicular axis theorem, iz would be simply ix plus iy. That is, the moment of inertia of the rigid body with respect to an axis which is perpendicular to the plane of the planar rigid body would be the summation of the moment of inertia of the rigid body or lamina with respect to two axes which are mutually perpendicular to each other and lying in the plane of the lamina. So this is pretty simple, straightforward and easy. That is, iz equal to ix plus iy. Now let us see that how do we prove this particular theorem. So let us assume that in this lamina we consider an elemental mass dm. Now this dm is located at a radial distance r from this point of intersection of all the three axes. Now let's say that the component of r along x-axis be x and the component of r along this y dash axis be y. Now clearly these two perpendicular axes x dash and y dash are mutually perpendicular to each other. That is, this particular angle is 90 degree. So by Pythagoras theorem we can simply write x square plus y square is equal to r square. Now, what is the moment of inertia of this elemental point was with respect to the zz dash axis? Let's call this as diz. So it would be simply dm times r square. So what would be the total moment of inertia of this laminar body with respect to the zz dash axis? It would be simply integral of diz, that is simply integral of dm r square. Similarly, what would be the moment of inertia of this laminar body with respect to the xx dash axis? Let's call this as ix. Ix would be simply integral of dm y square, as this elemental point mass is located at a distance of y from the xx dash axis. And similarly, iy would be integral of dm x square. So now let us take this particular expression and let us try to further simplify this. So iz is integral of dm r square. Now, as r square is equal to x square plus y square, we further simplify this expression as integral of dm x square plus y square. So this reduces as integral of dm x square plus integral of dm y square. Now, what is this integral of dm x square? This is nothing but iy. Now, what is this integral of dm y square? This is nothing but ix. So what do we get finally? We obtain finally that iz is nothing but ix plus iy. So we finally obtain iz is equal to ix plus iy. This is nothing but the perpendicular axis theorem. Now let us try to look at some applications of the perpendicular axis theorem. So let us start our discussion by looking at the case of a ring. So let us assume that we are given with a ring of mass m and radius r. So previously we have already calculated the moment of inertia of this particular ring with respect to this particular axis, and we found out the value to be mr square. Now we wish to calculate the moment of inertia of this ring with respect to this particular axis, or let's say this particular axis. So let us assume that the moment of inertia of this ring with respect to this axis be, let's say, I dash. As there is a symmetry in the ring, there is no difference between this particular axis and this particular axis, which are mutually perpendicular to each other. And both this axis and this axis are lying in the plane of the ring. So the moment of inertia of the ring with respect to this particular axis would also be I dash. So let us just name our axis for simplicity. Let's call this axis as xx dash, let's call this axis as yy dash, and let's call this axis as zz dash. So axis xx dash and yy dash are mutually perpendicular to each other and lying in the plane of the ring, and axis zz dash is passing through the point of intersection of xx dash and yy dash, and it is perpendicular to the plane of the ring. So by perpendicular axis theorem we can write iz is equal to ix plus iy. So what is iz? Iz is I, that is mr square. So mr square, and what is ix? Ix is I prime, and what is iy? Iy is also I prime. So what do we have? Twice of I prime is equal to mr square. So what is I prime? I prime is equal to mr square by 2. So the moment of inertia of this ring with respect to this axis, or let's say this axis, is given as mr square by 2. So we have found this very easily without starting our derivation from scratch. Now let us look at how do we calculate the moment of inertia of a disk with respect to this axis, or let's say this axis, using the perpendicular axis theorem. So let us assume that we have a disk of mass m and radius r, and we are given with two axes, x dash and y dash, which are lying in the plane of the disk and are mutually perpendicular to each other. And we have a third axis, z dash, which is passing through the point of intersection of these two particular axes and is perpendicular to the plane of the disk. So previously we have already calculated the moment of inertia of this disk with respect to the z dash axis, and this we obtained as mr square by 2. Now let us assume that the moment of inertia of this particular disk with respect to this particular axis, let's say y dash, be I prime. As the disk is completely symmetric, the moment of inertia of this disk with respect to this particular axis, x dash, would also be I prime. This is because there is literally no difference between the distribution of mass if we compare the mass distribution with respect to axis x dash and y dash. So according to perpendicular axis theorem, Iz would be Ix plus Iy. So what is Iz? Iz is I, and Ix is I prime, and Iy is also I prime. So what is I? It is mr square by 2 is equal to twice of I prime. So what is I prime? I prime is simply mr square by 4. So the moment of inertia of this disk with respect to this axis or this axis is simply mr square by 4. So this was pretty simple, easy and straightforward. Now let us try to extend our discussion further, and let's do something different. Let us try to calculate the moment of inertia of a thin rectangular plate with respect to this particular axis, which is perpendicular to the plane of the plate. So this particular axis is simply perpendicular to the plane of the plate, that is, it is perpendicular to the plane of the screen, that is, it is coming in the outwards direction, let's say. So we have two axes, x dash and y dash, which are mutually perpendicular to each other and intersecting at the center of this thin rectangular plate, and these are mutually perpendicular to each other. And there is a third axis, let's call this as z dash, which is passing through the point of intersection of these two axes, and it is perpendicular to the plane of this plate. And this plate is quite thin, that this thickness of this plate is very small. This is very less than L or B, or the thickness is tending to 0. So let us try to calculate the moment of inertia of this plate with respect to this particular axis. So from perpendicular axis theorem, we can write Iz is equal to Ix plus Iy. Now let us try to calculate Iy. So this is the y dash axis, this is the center. So we have previously studied that we can always shrink the dimension which is parallel to the axis of rotation. This is pretty straightforward. So what do we do is, for calculating Iy, we simply shrink this particular dimension, that is, we shrink this particular dimension b. So what does this plate reduce to? So this plate simply reduces to a rod of length L. Let us say that the mass of this plate was m, so the mass of this plate is m, so the mass of this rod would also be m. So now we have to calculate the moment of inertia of a rod with respect to its central axis, which is perpendicular to the length of the rod, and the mass of the rod is m and its length is L. So we have already calculated this result. So Iy is m L square by 12. Similarly, when we try to calculate the moment of inertia of this thin rectangular plate with respect to the xx dash axis, what are we going to do? We are going to again shrink the dimension which is parallel to the axis of rotation. That is, we are going to shrink this particular dimension. So what do we have? We are reduced with a rod of mass m and length b, and we wish to calculate the moment of inertia of this rod with respect to this particular axis which is passing through its center. So what is Ix? Ix is simply mb square by 12. So we have the values of Ix and Iy. So let us try and calculate the value of Iz. So Ix is mb square by 12, Iy is ml square by 12. So what is Iz? Iz is m by 12 times L square plus b square. So this is the moment of inertia of this thin rectangular plate with respect to an axis which is passing through its center and perpendicular to the plane of the plate. Simple, easy. Now let us try to do something more different in a smart way. Let us assume that we are given with a cuboid and we wish to calculate the moment of inertia of this cuboid with respect to an axis which is passing through its center and which is like this. So what do we do? As we have already stated this more than 50 times, that we can shrink this particular dimension which is parallel to the axis of rotation. That is, we are going to shrink this particular dimension which is the height of this cuboid. So what do we get? We get a thin rectangular plate of length L and breadth B, and the moment of inertia of this cuboid with respect to this axis is the same as the moment of inertia of this thin rectangular plate with respect to this particular axis. So if the mass of this cuboid is m, so the moment of inertia of this cuboid with respect to this particular axis would be simply m L square plus b square by 12. That is, the moment of inertia of this cuboid would be the same as the moment of inertia of this thin rectangular plate. So this was pretty simple and easy. So that's the strength of the perpendicular axis theorem and understanding the concepts in a smart manner.